recall that what we did. We defined first of all that what does this object means. Okay. In other words, what is the meaning of having an infinite series of real numbers. So we said that what is the meaning of this? The meaning of this is that you take the sequence Sn, which is the sequence of the partial sums. Okay, so it's like a finite sums, all possible finite sums. An, and so once you take this, obviously you're going to have a sequence of sums of the terms of the sequence, An. And if this sequence are really the limit of this sequence as n, I give that limit a name which is that is n equal to 1 to infinity. Okay, getting the point? So if I have a sequence, so we know what does this sequence mean, and we know what is the meaning of the limit of the sequence. Okay, so whatever the limit of this sequence is, we are going to name it that by this symbol. So we're going to call that as infinite series. So why I am doing it? I am doing it because I want to define this new object in the terms of something that we have defined previously. Because you can say that we haven't defined this yet. What is the meaning of saying that you have an infinite sum of numbers? Now I'm saying that the meaning of this is that imagine you have a sequence, you take the partial sums, and the sequence of partial sums, and the limit of the sequence of partial sums, I'm getting that difficult. And then I can define this notion that, this guy n equal to 1 to infinity, An is convergent. So it's convergent. When it is going to be convergent if this sequence, so it's like if this sequence of the partial sum converges.
Sir, limit between 0.
Huh?
I
So this sequence converges. Sequence of partial sum converges. Okay. So if this is converging to some number s, then we're going to say that this series is converging to that same number s. Okay. And we're going to say that this is divergent, obviously when this is. Okay. And then we quickly prove what you call the Cauchy criterion. Okay. The Cauchy criterion. The Cauchy criterion was that basically this sum An, where n goes to 1 to infinity, is convergent if and only if the tails of this sum basically, it's like which begins from some finite number, say n and nz m, ak, if and only if I should say, for every epsilon positive, there exists a natural number n such that this sum which begins from some fixed number n to not fixed, but like arbitrary number n to an arbitrary number m is less than epsilon, and for all n bigger than or equal to n bigger than or equal to. We saw that how you get this up. So we say that a sequence is convergent if this is convergent. And if this is convergent, then it must be Cauchy by the completeness problem. So if you have Cauchy, then it should satisfy what? That for every epsilon positive, there exists a capital N such that Sn minus Sm is less than epsilon. But if you take the Sm minus Sn or Sn minus Sm is going to be this or that. It's like a one-liner proof of this. And then we also did a quick result, and that quick result was, so the result itself does not seem interesting, but its contrapositive is very interesting actually. So the result was, okay, that if the series is converging and equal to 1 to infinity, okay, is convergent, then what? The limit n approaches to infinity of representative of sequence should go to 0. In other words, if a series is convergent, then its nth term or maybe the representative of the series should go to 0. So not something interesting when you see it forward, but it's very interesting when you see it contrapositively. Because what does it tell you? It tells you that you have a series and you want to know its convergence or divergence. First check that whether the limit of an goes to 0 or not. So if it is not going to 0, then it's certainly this is divergent. Okay? And hence because of that you call it divergence test. Right? Divergence test. I can use divergence test to have some immediate consequences. For example, I can say, so it's like, is this series convergent? What do you say that? Is it convergent or divergent? So your first attempt should be to see that whether it is divergent or not. Now what is an here? So the an is n squared, and you take limit n approaches to infinity, okay, and infinity is going to explode actually, okay, and therefore the series, this is obviously this condition is not satisfied, so this must be divergent. Okay. Interestingly, just think about it. Interestingly, something which is something like this. Imagine I have this series of 1 over 1 plus n here, n runs from 1 to infinity. Okay. Is this a divergent series or
Divergence.
easily say that now that's a divergence. Just apply that to the series. I mean, even
series or not convergence?
Here we have the same meaning. If it is not converging, then we're gonna say that it's divergent. In other words, this number, this sum can't be a finite number. This sum is going to explode. Even though the representative of sequence is convergent. Okay. So if an is convergent, it doesn't mean that the series represented by the an is going to be convergent. So it should converge to 0. Therefore, and you can see that actually. Just think about it. When you are saying this, what does it mean? When you are saying this, what does it mean? It means that those series are going to converge for which the representative is kind of a dying out. It's getting smaller and smaller and smaller as n gets bigger. Because if this happens, just think about it in this sum actually. What's going to happen? So it's like, okay, maybe the first terms have a higher magnitude of values, but as n will go to 0, okay, the contribution of the upcoming terms is going to be less and less and less and less. And hence you can say that yes, we can make sense of this series. Okay. But here, for example, why that looks like a divergent series? This looks like a divergent series because we say that every term is either 1 or close to 1 actually. So it's like a 1 or 1 plus actually. Are you getting the point? Okay. So it's like you are summing the one infinite number of times. Okay. obviously you can't control it. It should be huge. And should be huge. This is making sense. That is a sensible test. It makes sense. But does this say that this will be convergent if the representative is kind of dying out? So it's like vanishing to zero. And then goes to 2. And then goes. Okay? Let's move ahead. Can you give me the reasoning for this result? So I have this really small result, okay, which almost do not require proofs. Whatever you have learned previously about sequences and series, you should be able to answer. Yeah, sure. Hello. Once again. You want to see some real analysis? You must pop in.
I saw the formula is already.
Oh, it's like mind is started exploding now. Okay, thanks. Alright, so if I have, imagine I have a series of non-negative numbers. It's like I have a series, the n, where n goes from 1 to infinity and the n is bigger than or equal to 0 for all n. For all n. Now such series is convergent such a series is convergent if and only if the sequence of the partial sum. So whenever I will use Sn, I mean basically the sequence of the partial sum is bounded. Very easy. Is bounded. Why do you think that this should be? It's like if you have non-negative terms, in a sequence of non-negative integer or variable plus. So it's going to converge if and only if the sequence of partial sums is bounded. Why do you think this should be this?
So every convergent sequence is bounded.
Okay.
So partial sums is also a sequence. So it's a
So in other words, this can follow it.
yes.
Like
Directly
if
follows.
this sequence is convergent, so like this is convergent, okay, then the sequence of partial sums is a Cauchy sequence or a convergent sequence, and hence it must be bounded. So something very easy peasy. So the real riddle is to basically go backwards. So what do you think that if you have this, then
We never cut down for a sequence. It cannot be here somewhere.
okay.
Well, if we take the limit again, this the convergent probability is bound to happen anyway. At the end, we will some of
Anyway, so try to write.
Some can लेके सकते हैं since it's bounded and since a is greater than 0, so it's also increasing. So hence it's a monotonic bounded sequence. Thus it will converge.
Sn is bounded and
It's monotonic.
that's a good reason. So you have the monotonic convergence sequence. You say that Sn is bounded and And if all these are negative, non-negative, that means that you have A1. So it's like A1 plus A2 is going to be bigger than A1 and A1 plus A3 is going to be bigger than A3. Then SN must be monotone as well. So if it is monotone and bounded, so the MCT guarantees that it should converge. This should converge, enhance the series convergence. So you see that this follows from something. Interesting. So the next thing that I would like to prove is, something which you might have heard before, and which I say the mother of all tests for the series is that you have learned that. The rest are the basically corollaries of this book. That test is, what do you think? What should be your guess actually? So you must have learned loads of tests actually. The ratio test, root test, and comparison test, field test, this and that. What do you think? Which could be the mother of all?
I think rate of comparison.
Huh?
Rate of comparison.
It's like comparison test. The rest are just basically.
But sir, there are two things. One is comparison and other is ratio comparison.
I'm just not the comparison. So I'll call that comparison.
If there are one is data and less as well, then dependent on diversion.
It's going to be something similar. It's going to be something similar. So the comparison test is kind of a mother of all tests. It's going to prove the comparison test. It's like why this comparison test is not some kind of a God-given fact. So that's very good. From the things that we have defined there. Okay, so here the theorem, which we can treat as this. If An is less than or equal to Cn, we have two sequences. One is An, other is Cn, and one sequence, the absolute of ones, it's like one sequence is dominating other sequence. Okay? But for not all n, but for n bigger than or equal to n naught. So it's like after n naught, this is true. Where n naught is a natural number. Now, if Cn converges, then An converges. From now on, I will not write this, n equal to 1 to infinity. So it's like if I'm not writing it, you assume that it's there. If I have to write the index, I will write explicitly. If I'm not writing it, just assume that it's 1. So it's like one sequence is dominating other, and you have series. If the series of dominating sequence is converging, corresponding to the dominating sequence is converging, then the series, corresponding to the sequence An, which is dominated by Cn. So roughly like if the big series is converging, the small is also converging. That's the first part of this. The second part is that if you have Bn, An bigger than or equal to Bn, which are non-negative or non-negative. For all n bigger than or equal to n naught, and if the sum the n diverges, then the n diverges. Okay? So before getting into the proof, do you see, okay, can you see the relationship between statement A and B? In other words, can I, or more explicitly, do I need a, if I prove A, do I need a proof for B? Can you deduce B from A? Just take the counterpositive. Let's take the counterpositive. It's going to be essentially A. So here's the proof. So though it is counterpositive, but you must write it properly. Okay? So you have to write this proof. That's what it says. Okay? So that's assumption part. Okay? You shouldn't say if, the better is that if I say left. Because if part is last one. So my assumption is that this converges and I want to show that this is convergent. So whenever I want to show that something is convergent, what should I do? So I'm going to do what? I'm going to choose an epsilon. It's like epsilon game everywhere. So not choose, but give an epsilon positive, like for given epsilon positive, okay, will exist and one such that one. Like sum of k equal to 1 to m, and not 1 but n to m, Cn less than epsilon for all, and bigger than or equal to n, bigger than or equal to 1. Agreed? Okay? So now consider this. Right? So now consider this. So I would like to have a similar bound on A and I. So let's consider this.
Yes.
So I have k equal to 1 to m. Okay, before going to do that,
Choose your answer.
oh yes, we have to cleverly choose because I want this and this condition to be true simultaneously. So for that, I need to choose n, which is maximum of
N1 and N0.
n1 and not. So I'm going to say that for all m bigger than or equal to n, bigger than or equal to this capital M, okay, I'm gonna, we can have this, which is the sum of k equal to 1 to n, okay, of n to m, and then ak, where should I go next? Like,
Less than
C.
so you can apply the generalized triangle inequality, okay? Or you can directly use this one. So you can't use this unless you have an absolute or a. So you can apply the generalized triangle inequality. It's like k equal to n m, and you have the absolute of ak, okay? And this is less than or equal to what?
7.
What?
C K.
Equal to k equal to n m Ck, obviously this is greater less than 9. But if the mod is less than epsilon, then I can say that
this follows.
true as well. Mod of a number is always bigger than the equal to the very simple. Reality that appropriately. Is it making sense? Okay. So I'm leaving B as a gift for you to do it for yourself. But as you spotted already, that is just nothing, just a comes a positive off. Okay. Alright. And once you have this, what you call the mother of all tests, we can see actually that how everything else is going to follow from. Alright, so let's begin with something well known, which you have I learned in school time. Let's prove it. So if x is a number which is sitting between 0 and 1, strictly less than 1, then you're going to say that the sum of n equal to 0 to infinity x raised to n must be what? Must be 0. Is it? How about saying 1 over 1 minus x?
Yes, sir. David.
So in other words, if x is between 0 and 1, this is going to converge. And is going to converge 1 over 1 minus x. And what is the meaning of that this is converging to 1 over 1 minus x? It means that if you take the sequence of partial sums of this sequence, that sequence of partial sums is going to converge to inverse. And hence we say that the series is equal to 1 over 1. Okay. And if x is bigger than or equal to 1, then the series is going to explode. In other words, it's going to diverge. So it's parallel, right? Then series, the matrix series, is divergent. Okay? Alright, so what should I do? Help me out. Yeah. Okay. Let's assume this case basically. So if x is 1, what will happen? We'll have 1 plus 1 plus 1 plus 1. Okay. Or if x is 1, actually your an is 1 actually.
So the limit of it is not
So
0.
if an is 1, so it's like the sequence represented by
It's not
okay, is going to, it's not converging to 0 and hence the 0 by the divergence. Go back to n, which is x n, 1 to the n. How about if x is not 1? It's like greater than 1 or smaller than 1. What would be Sn in this case? less n. It's like sum of first n terms.
But it's going to be greater or less दोनों के
It's going to be
1 plus
one
x plus
plus
X power n.
the last term
x power x
x power
and
sure
and
x power n minus 1 x power
this is not